structures, and also I try to find opportunities in medical applications. So this is the topic for today's forum, exploring the frontier of acoustics. We are very happy to have Professor Ying from Nanjing University, Professor David Zheng from Nanyang Technological University, and also Professor Chris Kube from Penn State University as a speaker for today. And also we are happy to have Professor Zheng from Nanjing University and Professor Chang Su from Institute of Acoustics as our panelists. So I don't want to take too much time from our speakers. So let's welcome our first speaker for today. Before I give stage to David, I want to briefly introduce our first speaker, Professor Zheng Fan. So Dr. Fan is an associate professor in the School of Mechanical and Aerospace Engineer at Nanyang Technological University. He earned his PhD degree in mechanical engineering from Imperial College London in 2010, and his bachelor and master's degree in acoustics from Nanjing University. Currently, he leads a research team dedicated to developing novel technologies for non-destructive evaluation, structural health monitoring, and sound manipulation. His work integrates advanced physics and modeling technologies with the development of a method that can be rapidly deployed in practical settings. Dr. Fan maintains strong links with the global industries, collaborating with many major companies such as Rolls-Royce, Shell, and many other companies. He has published over 80 papers in top-tier journals, including Nature Communication, Physical Review Applied, and many other very famous journals. He holds 2 international patents and has successfully licensed these technologies to industrial partners. In 2018, Dr. Fan was awarded the Ultimate Medal for his outstanding contribution to structural health monitoring. In 2023, he was ranked among the world top 2 scientists by Stanford University. Dr. Fan served as associate editor for structural health monitoring and Ultrasonics, 2 leading journals in the field of ultrasonics and acoustics. Today, Dr. Fan will give us a talk on exploring the potential of ultrasound from defect imaging to particle manipulation. Dr. Fan, it's your stage.
Thank you, Yang. Can you all hear me?
Yes.
Okay, then I'll share my screen. Right, can you all see my screen?
Yes, we can see.
Okay, excellent. Thank you, Yang, for the introduction. So my name is Zheng Fan. I'm from Nanyang Technological University in Singapore. So today I'm going to give you a talk about exploring the potential of ultrasound from defect imaging to particle manipulation. So as Yang just introduced, I'm associate professor at NTU Singapore. I got my PhD at Imperial College. I'm also associate editor for 2 journals in our field. I also lead a team about more than 10 people, including researcher staff and PhD students, including some visiting PhD students in the CSC scheme. Okay, so I would like to start with this slide saying, okay, because my main research area is about ultrasound, or is a part of the acoustic scheme, but in the frequency higher than 20 kilohertz. So I would like to say something about what can we do with ultrasound. Broadly, I would like to divide it into two catalogs. One is like ultrasound will be able to convey information. It carries some information. Like we are in the nature, we know dolphins, bats can use ultrasound to communicate with each other, or using ultrasound to identify the objects around them. By interpreting the echoes coming from the objects around them, they are able to identify whether these are enemies or their food, right? So in the industries, we are doing something very similar. We are sending ultrasound to the objects or to a medium. This medium has certain informations. This medium could have some complex material properties, could have cracks, could have voids in the medium, or could have complex like different crystal orientations in the medium. Then when we send an ultrasound, it would carry this information of this medium, and this ultrasonic signal will be encoded by these informations in the media. So the objective of us is how to make these information available for interpretations, like how we can reconstruct those informations from these signals. So typically we can use in certain ways, like using analytical methods or using numerical methods, or even using AI-driven methods that we can do some kind of reconstructions that we can retract the information from ultrasound. Right. So this is one of the main areas that we see that very often in medical field, people using ultrasound to check the health of a person, of a patient, or people using NDT like what we do. We send ultrasound to check for abnormalities in the materials. So that's we are using one part of ultrasound. Let me get my pointer. Okay, this is one part of ultrasound. Another part of ultrasound application is that we can use certain energy information in the ultrasound. The ultrasound, as we know, it carries the mechanical energies. It has a vibration, it has mechanical energies. Then somehow we can explore or harvest those energies and then transfer these energies to certain other areas or other form of energies. I took a few pictures, some of them I generated from ChatGPT this afternoon. So I hope you could see it could mean something. So one is like we can using ultrasound, high intensive focused ultrasound to do some therapies in medical field. So we can somehow transfer the energy of ultrasound from this mechanical energy to heat, right? So this could help to relaxing the muscles, or could help to killing the cancer cells. That's one of the applications. Another application is that we can using ultrasound, the energy into ultrasound into the water, and it will create the bubble for the bubble to oscillate. These will help to do some ultrasound cleaning. And these cavitation of the bubbles will help to remove those dirts from the objects. So these we do as cleaning. Another part of application is that we can using ultrasound to do welding. We have pretty high power of ultrasound, and this ultrasound energy can be used to melt those metals and to fuse those wires together, as we often see those wires in the widely applied in the electrical vehicle sectors. There's a lot of these wires, and to bond these wires together, typically we can using ultrasound to fuse them together, right? So that's one of the application. And last but not least, we can also using ultrasound and transfer this energy to trap particles. We call it as a particle manipulation or acoustic tweezing. So the idea is that we can using ultrasound to create a potential well, and this potential well will be able to trap particles, and then we can further, since it has been trapped, we can further manipulate these particles for different positions and create some patterns from these particles. Okay, so that's something in general I would say what ultrasound can do from my understanding. And this also fits in the outline as my talk. My talk will be two parts. One is we want to try to use ultrasound to reconstruct some information inside material, including material properties or including defects. Another side of my talk will be how to transfer the energy. We will show you how we can use ultrasound to create a potential well, and that can trap the particles. Okay, so let's talk about how to use ultrasound to extract information from the material. So let's start with an example that we commonly see in the structures around us. We know the structures that will get degradation over the years, and there will be certain defects or could be cracks coming from the fatigue loading, or that we could have like corrosions from the environment or from the chemicals the pipe is carried. So these kind of defects will happen over the years, and the defects will grow over the years, right? So the objective of our non-destructive testing person is try to use certain means. That means could be ultrasound to localize the defect, to say whether there's a defect or not, right? So this is the first objective. Then the second one is, once we know there's a defect, can we use ultrasound to further diagnose this defect? Like as we are patient, we go to the hospital, we want the doctor to diagnose how serious is our disease, right? So similarly, in NDT, we're using ultrasound to diagnose how severe is the defect. So typically, that involves how to resize the defect, how do we characterize the defect. That we call the diagnosis of the defect. And then using this information, we can pass this information to the fracture mechanics people for the prognosis, like once there's a defect, how long this structure can last. And that's the information that people are very concerned, right? So that we are saying that we can using ultrasound to characterize defect for component sensing. So that's our objective for that. And then in order to characterize defect, there are a few methodologies that can be used. So first, we can using amplitude-based method. That's very simple to understand. So we send an ultrasound and we find reflections from certain defect. If the amplitude is large, that means the defect is potentially has a very big defect. This we call it as an amplitude and based method. If the amplitude is low, that the defect could be potentially small, right? So that's pretty straightforward. Like using amplitude method. We can also using time-based method. So for example, the defect, for example, cracks can have diffractions, and these diffractive signal can arrive to the detectors, and we'll be able to measure the travel time difference between the diffractive signals. And then from this information, we will be able to measure the difference between different tip diffractions, and then hence we will be able to know how severe or how long is the defect. So we call it as a time-based technique, right? So this is often used in like weld inspection. We call it time of flight diffraction method, TOFT. Or we can using image-based method. It's very commonly used nowadays using array transducers. We send an array transducers after beamforming, it's able to focus at different positions in the medium, and by detecting these different scatters will reflect the ultrasound, and then we'll be able to generate image based on the defect position and defect shapes. So by reading at the image, some people can somehow tell where is the defect and how big is the defect, right? So that's the image-based method. And the last method we want to say is like we can using inversion-based method. So that's less based on, for example, if you have a structure with certain defects, we can create a certain forward model techniques that's able to predict what ultrasound signal would look like when it goes through a certain medium that could have a defect or may not have defect. And then we will be able to compare the predicted signals with the actual measured signals. Obviously, if there's a difference between the prediction and the measurement, the signal won't agree with each other. Then we can further iteratively improve our material map or whatever map. And this map iterative process will, in the end, give us an inverted or reconstructed material map, right? So that's, we call it as an inversion method that can be used to indicate flow properties. So that's something in general. And then how to accurately characterize real defects. We can, in general, what we need is we can have more information from the defect, or we can have better imaging algorithms. So this is the analog that we can go to hospital. We use X-ray CT, the X-ray computer tomography. We can form a three-dimensional images from a patient, right? So this idea is like you can have X-ray go through the patient, and then by detecting this X-ray absorption of the X-ray, you can generate image, and then this X-ray can rotate 360 degrees, and by this rotation, we will be able to get a three-dimensional image. And can we do that with ultrasound? I think the answer is obviously yes. We can do ultrasound tomography. So this is one of the research work that our group has done, try to using ultrasound guided wave to map for corrosions. So this, I have an image here that shows in a big panel, you may have corrosion defects around the middle, and then we can have a transducer ring around this corrosion patch. And each of the transducer is going to send an ultrasonic signal. So this ultrasonic signal is particularly in the low frequency range, a few tens of kilohertz up to 100 kilohertz. This is very low frequency. And for ultrasonic guided wave, this velocity would change with the frequency thickness product. So when this ultrasound is going through this area we consider there's a corrosion or material loss. Obviously, with these corrosions, we manufacture this corrosion by ourselves. And when it goes to these areas, it will be received by transducers in the opposite area, right? So this corrosion patch will be able to scatter the sound. And these scattered sound would carry the information of this corrosion patch. And then from some inversion algorithms, then we are able to reconstruct what's the velocity map around this region. And from the velocity map, we are able to get the thickness map. So this is some general idea. I'm not going to go into the details of the exact inversion technique, but I'm going to show you some results. So this is after certain hours, I think after 74 hours of accelerated corrosion. This blue line is what we measure using laser, and this red line is what we can do inversion using ultrasonic waves. I see pretty good match. And then this is a line that we can do a monitoring. So we can do further monitoring of thickness, remaining thickness over time. So at one period of time, we'll be able to get what's the minimum thickness, right? And if we connected all these points together, we'll get a trend. We'll get a trend that shows at these corrosion speeds, so what can we predict from ultrasound? So this is actually quite interesting for the industries, because assuming that we can put some certain sensors around certain regions that is able to tell the corrosion rate, though that means the reduction rate, that potentially can give industry some useful information like how long your pipeline can be last if it is under a certain corrosion rate, right? So if this technique works, that potentially can help the industry. So this one was demonstrated in a plate, but of course we also do that in the pipeline, which is also very useful in certain industries because corrosion typically happens at these supporting areas or at around the bending areas at the pipeline. We do that on site, and then we put our transducer arrays at two sections of the pipeline and doing reconstructions, and then to get similar material loss of thickness loss at this hotspot. Okay, so this is one of the first method that we show that ultrasound will carry information and can be used to reconstruct the thickness map. So the next one I would like to say is just now we are using ultrasound guided wave, which is typically a low frequency wave, dispersive, but we can also using more traditional bulk wave. So this is a shear wave or longitudinal wave in the megahertz range. So in this, we are using ultrasonic bulk waves, and we are trying different ultrasonic imaging method for a complex shape defect. So through our research area, so NDT, many of us are looking at very simple defect like a hole or slot, but in reality, we know that the cracks could be more complicated. Like we could have a branch defects or have those complex shaped defects. And then for these complex defects, typically to get information from that or to get as much information as possible from this defect could be challenging. So in this work, we are trying different imaging methods. So this is a lot of people is using what we call total focusing method to try to image this defect. And we also borrow some image algorithm from geophysics area, elastic reverse time migration method. So we're testing different methodologies, and then our objective is to extract or reconstruct as much information as possible, i.e. we want to get those features, those branch features, and also these features to appear, right, as much as possible. So this showcase certain results. The comparison with TFM shows this RTM imaging has a certain advantage in that. Right. Just now we're talking about defects. It's more about two-dimensional defects, but we also can use our ultrasonic imaging for three-dimensional defects because we know that cracks are mainly three-dimensional, not two-dimensional case. So in this scenario, we need to get the information from the third dimension, right? So the way we do is we have an ultrasonic array. So this is still a linear ultrasonic array. And using this linear ultrasonic array, we can extract information from this plane. So this plan, we use a traditional half-skip total focusing method to get the information in this plan. And then because the defect is three-dimensional, we scan these transducer along the third dimension. And then, of course, we are not only stitching the images together, but also we apply certain imaging algorithm. Like in this case, we using synthetic focusing method, synthetic aperture focusing method, to do this the third dimensional imaging. So this shows a few defects in the simulation as well as in experiment. And also we are doing experiment with some complex shape defect. This is a real fatigue defect coming from thermal fatigue loading. And then we are, with our imaging method, we are able to relatively accurately to reconstruct these defects using the methodology we developed. Okay, so that's for a three-dimensional defect case. The next thing I want to say is we can also using ultrasound for surface that is complex. So just now, I demonstrate a few cases that the surface is relatively smooth, right, or a plane, a very smooth surface. But in reality, we may have surface have very, very complex shapes. And for this complex shape of defect to get inspect those defects inside these surfaces could be challenging. And in this work, we develop certain techniques we can using exploring laser ultrasound. Using the laser ultrasound, the advantage of using laser ultrasound, we are able to generate multiple modes. So one of the laser mode is a generated ultrasonic mode is a surface wave that will be able to claw around the surface of the structures. And then we use this surface clawing information to reconstruct the profile of the surface, and then use this profile information, and then together with a longitudinal mode that a laser ultrasound is able to generate to do focusing, right? So to do total focusing. So with this way, we are able to reconstruct defects in a complex surface. Okay, so that's one of the work that we have done. This is the simulation work, and this is the experimental work. And we can also using laser ultrasound to generate a surface clawing defect, surface clawing mode. That mode will be able to claw around those slots or cracks that that can claw around that, and then we can use the information that is coming from this ultrasound. So you see this ultrasound is clawing around along the defect, and then by detecting the reflection of this ultrasound, obviously we are able to reconstruct what is the length of the defect. So this is another work that we have done for the surface slot characterization. Okay, so earlier what we say is, although it's a complex surface or complex shape of defect, but the medium or the material we are using is relatively simple. We're using aluminum or some metals, which has very small grain size, and we can consider it as isotropic and homogeneous media. Right? But in certain scenarios, the medium could be much more complex. For example, here in this case, we can do something with the concrete. Concrete is typically something because of the aggregates, because of the rebars, it has very complex material properties. And then it does have certain issues with certain issues with the concrete. For example, the concrete, the rebar could get corroded. So one of the issues in Singapore is like we are in the high temperature, high humidity environment, and the concrete do tend to corrode very fast. And when this concrete start to corrode, you will have rust growing around the concrete. And these rust will basically squeeze the concrete and you will form a crack, right? The crack will grow from the rebar and grow towards the surface. So in this work, we are hoping to using one of the ultrasonic wave to tell how severe is these cracks with respect to the surface, how far away these tips away from the surface. So the idea we are exploring is that we are using ultrasonic Rayleigh wave, which we know that the energy of the Rayleigh wave is focusing around one wavelength of its spectrum, right? So that we are able to use the information. So if we are able to send a Rayleigh wave with relatively broadband, then by looking at looking at the spectrum of reflected signal, we will be able to tell which part of the spectrum has been blocked by these defect. And using this information, we will be able to tell how far away is this tip from the surface, and then somehow correlate with the corrosion levels. Right? So these are some research work we just published last year. And we do some corrosion map from somewhere around the rebar, and these are the comparison between these images and those crack images. Right? So this is a pretty good agreement. So this is like we can tell how far away is the crack, but we can also using certain information from ultrasound to extract the tip information further. So this is the information we try to use ultrasound, which are encoded in the later arrival part of the signal. So a lot of the research work, most of the time we are using the first arrival. So this always carries the reflected signal. But we know that these later arrived signals, we call it coda wave, will also contain certain information, especially in this scenario. The material has complex material properties, has a lot of scatters like aggregate, then the ultrasound will have multiple scattering in this medium. And these multiple scattering will be interacted with the cracks, which is basically connected with the rebar, right? So by imaging the scattering cross section, we are able to tell we are able to form an image that is able to that is going to give us the information of the crack. And these information of the crack basically can tell us how far away is the tip with respect to the rebar. Okay, we did some work in the simulation, and we also compare with some X-ray images. So this is our prediction, and these the crack is highlighted by these red lines. So this we can see reasonably accurate prediction has been achieved in this prediction of crack in complex medium. So this is one type of complex medium. Another type of complex medium is we can using ultrasound to further explore the imaging in the wavy structures in a composite. So we know composite is a typical complex medium. It has anisotropic material properties and could be inhomogeneous because it has different layers. Different layers can have different patterns. And then it do have a lot of issues with the composite structures, like these alignments of this plier could be misaligned or could be distorted, and these will obviously affect the performance of ultrasound. So in our recent work, it actually just published this year. So we are trying to using ultrasound to reconstruct the plier information along the thickness. So we are using ultrasound. We are together with 2D analytic signal techniques. We are able to not only extract the phase information, but also the frequency information. We are able to get the plier alignment at different locations. So that's something we did quite recently. Right. For the ultrasonic imaging part, the last thing I want to share is about we can using ultrasound to reconstruct microstructures in polycrystals, which is like one of the typical materials the industry is using, polycrystals. So a typical way for the material people, in order to understand the properties in polycrystals, they need to do material studies. The tools for material studies, including SEM or EBSD, electron backscatter diffraction method, for example. But these methods, obviously, they only detect surface, and it's very tedious. It only takes very small samples at each time. So in this work, we are trying to explore whether we can using ultrasound to reconstruct certain microstructure information in the grain, relatively big grain, of course, for the ultrasound wavelengths-ish matter. So whether we can using ultrasound to reconstruct those material information or microstructure information from that. So the way that we applied is that we send an ultrasonic surface wave, so on a relatively smooth surface. So when the ultrasonic surface wave is going through this media, it will interact with those grain structures, right? So with polycrystals, different textures, it will interact with that. And then these boundaries of the crystals will be able to scatter ultrasound, right? These scattered information, if we are able to capture, then obviously it contains the information of the grain boundaries. And also, if we can measure the ultrasonic propagation at different angles, we are able to get what's the velocity of ultrasound at different areas. Right? And this information may not be straightforward to reconstruct, because a lot of the time this information will be able to will exist in the form of evanescent wave, in which the wave does not the wave exists, but it does not propagate very far. So in order to do this reconstruction, we do ultrasonic scanning at each point. So we send an ultrasonic wave on the surface, a surface wave, and then if we are able to use, for example, laser vibrometer to pick up the local ultrasonic waveform at each individual point, and then by doing certain reconstructions, we are able to capture the evanescent wave, and using this evanescent wave, we will be able to reconstruct the grain boundary. And also, this is one thing, and also we are able to reconstruct the velocity of Rayleigh waves, which the velocity of Rayleigh waves somehow tells certain information of the texture. And this is our experimental setup. We have our ultrasonic pulsar sending a Rayleigh wave on the surface, and this Rayleigh wave will be able to propagate in this part, and then we have a laser Doppler vibrometer to scan the sample, right? And then this is our reconstructed results. So this is some simulation results. We also have experimental results. I think this one looks better. So this one shows that using evanescent wave, we are be able to reconstruct the surface of the boundary. For by the way, this is the actual boundary of a sample that we are tested from the direct energy deposition method, additive manufacturing, one of the additive manufacturing methods. So this shows the grain boundary can be reconstructed quite smoothly, and this image shows the velocity can be reasonably good, can be reconstructed in a reasonably good way. Okay, so that's we demonstrate that ultrasound. We can using ultrasound to reconstruct information from defects, and then we also demonstrate we can using ultrasound to reconstruct information for material properties. Okay, so that is one of the area that I want to talk. I still have some time. I want to share another part of ultrasonic application, that we are harvesting the energy. So that is another, I think it's a very important part, but we have done certain work in this part I would like to share. So in this work, we are trying to use ultrasound to create a potential well. So this is the setup. We have the transducer, which will send a plane wave to the medium. This is a plane wave from a normal PZT transducer, and then on top of the transducer, we create a lens. This lens is made of some silicon materials that has very close acoustic impedance compared to water, so you minimize the attenuation in this lens. So this lens has a particular shape. You can see this is the quite funny shape, and from this shape of the transducer, it will control the phase of the ultrasonic wave when it's exiting from the lens. So we design in the way, so this is the phase information. We design two phase information. So one information of the phase is that it would focus at particular locations away from the transducer. So we call it focusing. So we can create a focusing part. At the same time, we can also have the phase to rotate 300 from -pi to pi around this circumferentially, so that using this way we are able to get the phase when the phase is exiting is like this shape, right? So for this shape, when we introduce into the fluid medium, it would create a vortex. So we call it as a acoustic vortex. So this acoustic vortex will create a potential well here. So this potential well will be able to levitate particles, to trap particles, and then at the same time will create acoustic streaming flow. To demonstrate that, so this is a design of this of this lens, and this is a demonstration experiment. We have our lens and the piezo, so we put in a scanning arm, and then we have a camera to shoot at this area. So, and we also have the lens to do PIV studies to study the flow around this particle. I'm going to show you a few videos that shows this lens. So this is the lens, and this is the particle. We are showing this can be clearly trapped. So this shows when the lens is moving horizontally, it creates a potential well. You can see when the lens is moving, the particle is following, right? So this is clearly you create a potential well, it is able to trap. And then not only moving horizontally, it can also moving vertically. So you can see that the particle is going up and down, right? So we are moving up. And we can also do tilting. So you can see this still follows. So when we are changing the angle of the lens. And then we also try disturbance. Like here, we are creating potential well. We can see the potential well is very consistent. Even we have our plies put near the potential well, is still the ultrasonic the ultrasonic field will be able to penetrate from these objectives and then still create a potential well. So this is the very clear trapping. And then not only sphere particles, even the particles in non-sphere. In this case, we put two particles together, and you see that it can still trapped and get rotated, spinning. Right? And then these are the relatively small particles, and we can create a relatively large particles. In terms of the wavelengths, we have 2 times the wavelengths. So we will see that it can clearly trap even the particle is very large. And we do further studies in this velocity field, and then we look at rotation of the particles. We study some physics behind. We try to analyze the forces which is act on the particles. It's quite complicated. We have the gravity force, buoyancy force, acoustic radiation force coming from the transducer. Also, the particle is spinning. It has magnet force, right, and a friction force, and the flow would have drag. All these forces will basically balance in the end, and this balance will make these particles self-stabilized. Okay, I think that's all I want to share. Just to make a summary of my presentation. So we have demonstrated using ultrasonic techniques to characterize complex shape defects using bulk wave, guided wave, Rayleigh wave, and Kodak wave. And we have also using ultrasonic surface wave to reconstruct microstructural features of polycrystals. We can using ultrasound to manipulate particles through the mechanical energy. So that's all I want to share. Last but not least, I would like to thank all my team. Without them, no research can be done without these members. Thank you very much. I hope I follow the time.
Okay, thanks, David. And now we can move. Yeah, so we can move to the next speaker first, then we can have discussion in the panelist, okay? So the next speaker is Christopher Michael Kube. Chris joined the Engineering Science and the Mechanics Department at Penn State University in 2019, and his current research interest also focus on the ultrasonic non-destructive evaluation applications in additive manufacturing. Now, up to date, his academic contributions include over 47 published peer-reviewed journal articles, and his innovative research has been recognized with awards such as the Young NDT Professional Award and the Research in Non-Destructive Evaluation Outstanding Journal Article and the R. Bruce Lindsay Award from the Acoustic Society of America. So, Chris, are you ready? Hello?
Yep. Yes, I'm ready. Thank you.
Okay, thank you.
Go ahead and share my screen. Okay, so hopefully my screen is clear.
Yeah, sure.
Okay, so I'm going to start on this slide. And so David actually gave me a good transition into my talk. And I want to highlight that acoustics is very interconnected with the medium that is propagating through. So he gave a number of examples from composites and metals and water and air, where acoustics can propagate and carry the information about those mediums. So in my talk, this talk is going to be about looking at how acoustics propagates in 3D printed metals and additively manufactured metals. So there's a lot of hype around 3D printing metals, This is an example of a vehicle or a car prototype that was 3D printed. So very large structures with very fine detail. So one of the things that's holding 3D printed metals back is defects, such as porosity that forms. And why that happens is because metal 3D printing is essentially a welding process, right? So there's little tiny melt pools and welds that happen point by point and then layer by layer that builds up your part. So when there's a weld, the quality of the weld depends on how the weld solidifies and fuses and whether there's defects or pores inside that weld. So I like using this example. So this is a 125 millimeter cube of stainless steel that was 3D printed. So this cube was printed line by line and built up layer by layer. So if you go through the process here, you can calculate how long the weld is in this very small cube. This cube fits in the palm of my hand. It's 125 miles, right? So there's a lot of welding and fusing that has to happen, and there's a lot of potential for defects. Okay, so just a little bit of background on that. So I'll get into the meat of my talk here. So I mentioned melt pools. So melt pools are at the heart of this. A melt pool is the liquid region that forms due to the laser interacting with the material and melting it locally. So this is actually a cross-section image of the melt pool, or one flavor of a melt pool. This is taken from an X-ray image at a synchrotron source, and I'll be talking about this more later. So this is a high enough X-ray where you can actually see the melt pool and the weld. There's a liquid region that is contained within this part. And then this area in here is actually vapor or gas. So the laser that is creating the melt pool has enough energy where it actually boils the metal and it can create gas inside of the melt pool. So typically we don't want this gas. So this gas leads to bubbles, and then when the metal solidifies, it leads to pores, and that leads to defects in your material, and it reduces the properties of your 3D printed metal part. So in this talk, I'm going to be talking about how we're using ultrasound to study the fundamental dynamics of these melt pools. Excuse me. Okay. So to motivate this research, I like to put forward a number of questions and thinking about how we can use acoustics or how we can use ultrasound to study this area of very exciting research on the 3D printing or the additive manufacturing frontier. So some of the questions that I'm asking and my students and my researchers are trying to answer is, can we use acoustics to understand melt pool dynamics? So how does that melt pool fluctuate when the laser's on, right? That's going to influence how it solidifies and how defects form. Can we use acoustics to measure the melt pool dimensions or the melt pool shape? Can we use acoustics to measure the solidification rate? So the solidification rate is how fast your liquid melt pool solidifies. So think about placing a cup of water in your freezer, you get a solidification front, and that front moves along. And how that material solidifies dictates a lot of the properties. Can we use acoustics to sense cracking? So during this solidification, there can be huge stress buildup that leads to cracking, and we certainly don't want cracks in our 3D printed metal parts, especially if we want to have parts that are making automobiles or vehicles someday that have to drive people around. Can we use it to sense pore formation, the microstructure formation? So David had a nice picture of a polycrystalline metal microstructure. so we could actually sense how this forms in real time rather than looking at it after the fact. Can we use this sensing to determine the optimal parameters? So optimal parameters means these are the settings on your 3D printer that leads to a good part. So if we can understand the foundation of the process well enough, can we use that as a feedback mechanism to fine-tune the process such that we don't have defects to begin with? Can we use this sensing to assess the printability of new alloys? So currently, there's probably maybe 50 or maybe 100 alloys that could be printed, because out of the 50,000 or so alloys out there, very few of them we know how to print with, because they can crack or form defects and things like that. So the more studies that we have in this direction is going to open the door for printing new alloys. And then our group is working on computational models for the 3D printing process, and we could potentially use this sensing to validate those models. So one example of a computational model, and this will give you some idea of what the melt pool looks like. So this is the simulation in powder bed fusion. There's powder on top of a substrate, and there's going to be a laser that comes and melts the powder. And then you see this big sphere. The sphere represents what's called a spatter particle. And during these processes, you can have powder and liquid that gets ejected out of a melt pool that falls somewhere else. And then that gets in the way of the laser at various locations. This is a simulation that shows the heating and the melt pool. You can see the melt pool here. Suddenly it hits a spatter particle. It blows it away. But think about what's happening underneath the spatter particle, right? There's a very, very shallow melt pool. So the melt pool will likely not reach the next layer. And so you're going to get very poor fusion at that location. So we can use acoustics to measure potentially the melt pool depth when there's a spatter particle, and better understand how the material is fusing together. Okay, so that's a little bit of background. This is a very hot topic of research, and a lot of the fundamental melt pool research takes place at synchrotron X-ray sources. So this is the Advanced Photon Source in Chicago. In this facility, there's electrons that get accelerated around this ring, and as it's constantly turning, these electrons are constantly turning, it spits off X-rays tangentially into these little laboratories, right? Little is relative. This whole thing is, I think, 1.5 kilometers in diameter, and very high energy X-rays get spit off into here, and we use those X-rays to study the melt pool dynamics, right? This is what this is a schematic of how the X-rays work. And so there's an X-ray beam that comes off of that circular ring. It passes through a thin sample, and it projects your melt pool onto a detector. And that's exactly what you're looking at over here. So if you go to your doctor and you get an X-ray, typically they're taking one image, one frame, right? And you can see your broken bone. Hopefully it's not too bad of a broken bone when you do that. But at this facility, they can capture X-ray frames fast enough at hundreds of kilohertz of frame rate, where you can actually see the melt pool dynamics. And so you can see the time scale here is in microseconds. And then the scientists that did these experiments, they can isolate the region where you have liquid. And so this is liquid metal, liquid titanium metal, and then the gaseous region, which is within the blue. Okay. So these facilities have been used to study and determine optimal printing parameters for 3D printed metals. So two of the, I would say the most important printing parameters are the laser power and how fast that laser is moving to create your part, the velocity. And so at the synchrotron using the X-rays, they can image at different power and velocity combinations and try to figure out where you have the best melt pools. Okay. And that's kind of a first guess to the optimal process parameters that will lead to a good final part. So these are very fundamental studies. I call these parametric studies, where you're making a measurement with different power and speed combinations. There's a lot of research that happens at a part scale. It's a lot of mechanical testing of 3D printed coupons or 3D printed parts. A lot of process development happens here. And all of this is geared towards making a high quality part that we can trust and understand its performance. Okay, so I like using an analogy with medicine, and this is where there's kind of a gap in the 3D printing science and the manufacturing science. In medicine, we start with parametric studies. So if you look at pharmaceutical companies, they use these multiple well plates to study how various numbers of components of drugs interact, right? So you're mixing 2 parts of one drug, 3 parts of another. How does it interact? Is there a high potential for success, right? And so you learn a lot at this very early stage, right? Then a drug is promising, it goes to clinical trials. We use clinical trials to determine if it's safe, and then we finally have a product with hopefully good efficacy. So how well it works to treat the ailment with known side effects, right? So this is the analogy and direction that I think 3D printing needs to go, except this part over here can only be done at high energy X-ray sources, right? And very few people have access to do these studies, as opposed to this, that your multiple weld plate, any chemistry lab in any university or pharmaceutical company has the ability to test many combinations of drugs. So what we're looking at is, how do we enable higher throughput, right? So how can we do measurements like this level of fidelity at every lab in the country that does 3D printing? And our solution is to use acoustics or ultrasonics. So now I'm going to move into the ultrasound side of the talk. In this image, this is the inside of a metal 3D printer. Inside of this, we manufactured a cavity where we place ultrasonic sensors, and we can use sensors like this to monitor the melt pools or monitor the parts that are being built on top of this substrate. So there's another substrate that sits inside of this, where the ultrasound sensors are completely enclosed, and the ultrasound propagates upwards, and it scatters reflects from the melt pools or from the features in your part. So acknowledge the collaborators here. A lot of help has went into this, from the X-ray synchrotron scientists to material science scientists, and so forth. Okay, so I'm going to get into how this works, and I'll try to explain this in a very simple way. When we have an acoustic wave or an ultrasound wave that's propagating in a medium, I'll call it medium 1. This could be metal or water. And then all of a sudden there's an interface. This interface separates medium 1 from medium 2. This medium 2 has different acoustical properties. It has a different density and a different speed of sound, right? So when this incident wave happens upon the interface, we could get a reflected wave and we could get a transmitted wave, right? Whenever we have this interface, we can have the possibility of some scattering or reflection. So how does this work for the melt pool case? And so I want to bring back the image here. So keep in mind that the red line is the line that separates the solid part from your liquid phase, or the liquid region inside of your melt pool. And so ask yourself, you expect that the liquid region is going to have a different acoustical property than the solid region. And hopefully you're convinced that's the case. And so this boundary in the red line represents an acoustic impedance where we can scatter the ultrasound. And that scattered ultrasound is going to carry the characteristics of the melt pool. Okay. So that's the approach that we use. One fine detail that I want to highlight is that we use a shear wave. So shear waves, without going into a huge amount of detail, shear waves can't propagate into a liquid. Liquids can't hold and restore shear deformation. And so when a shear wave is in the solid, so shear waves propagate very well in solids. When it comes upon the solid liquid boundary, very little of its energy can go into the liquid phase. That means almost all of the energy is reflected or scattered. And so that is a big secret to the technique. So a little analogy to help you understand our results. And so I want to take you to another flavor of acoustics, and this is the acoustics in the air, right? And I'm eventually going to tie this back into the melt pools. So bear with me for a second. So this is an analogy that is taught to young school children, at least in the US. And I want you to imagine that you're sitting on a beach, and off in the distance, you see a storm, right? And lightning strikes, and you can hear the thunder. So what you can do is, if you see a lightning strike, you can start counting in your head, right? 1 second, 2 second, 3 second, 4 second, 5 second. Then eventually that acoustic wave reaches your ear and say 5 seconds. And you want to figure out how far away was that lightning strike, right? So what you can do is take that 5 seconds, you can multiply that by the speed of sound in air, so roughly 330 meters per second. And that works out to be about 1,600 meters, so 1,600 meters. And so you can use that to say, oh, that lightning strike is so far away from you. Maybe we can hang out at the beach a little bit longer. And then the storm is coming closer. And so you see another lightning strike, you count fewer seconds. You see another lightning strike, fewer seconds. So in this simple analogy, we had 3 events, so 3 different occurrences of an acoustic wave that we plot from t equals 0 to whatever arrival time that you hear at your ear. And so we can plot this like you see here, the 3 different signals. You have arrival time of the thunder. This is the number of seconds that you counted. And then on the horizontal axis, or the x-axis, we have storm getting closer. This might be on the order of minutes because the storm is coming at a much slower rate. And so we can look at this and see that if we see this downward trend, that means that the storm is getting closer. Okay, so hopefully everyone can follow me up to this point. And so what does this have to do with melt pools and 3D printing and ultrasound? So I'm going to show some results that look somewhat similar to this, the similar trends. And I'm going to be plotting the arrival time of ultrasound, and that's going to be microseconds. And I'm going to be looking at another scale, and that's going to be the melt pool. So if the melt pool is getting closer to the ultrasonic sensor, it's expected to have this behavior, right? Just like when the storm is getting closer, you see a decrease in the travel time of the wave. When we have a melt pool getting closer to our sensor, we're going to see this similar decrease. Okay, so keep this image in your mind. This is going to be very important when seeing the results. Okay, so now I'm going to show some results of ultrasound that was introduced into the high-speed X-ray imaging at the Advanced Photon Source in Chicago. That's the same synchrotron that I highlighted earlier in my talk. So to give you a little bit of background on the setup, this configuration was specially configured for the synchrotron. So I want to highlight the yellow beam here. The yellow beam represents the X-ray. It's passing through the melt region. So the melting is happening because we have a high power laser that's coming down and melting the top of your material. So the X-ray comes through and projects the cross section of the melt pool, so you can see that. And then what surrounds this is a cavity of water. So we use water to couple the high frequency ultrasound. And then these silver pistons are the ultrasonic sources that can both send and receive the ultrasonic response. So these are configured in a very special way such that we can get shear waves inside of the aluminum sample. And those shear waves focus right where the melt pool is. Okay. And this is the actual device that we use. This is after the water was drained. You can see the ultrasonic sensors around here, and they're all targeting a melt pool on the surface, about 200 microns beneath the surface on the sample. And this is a schematic that you see. So you can kind of see the focusing of the ultrasound, so that increases our sensitivity to the melt pool. And then you can see the water level that's beneath the X-ray beam. So before I get to results, I want to make one note about timing and synchronization. We're doing this at the Advanced Photon Source, the X-ray facility, so that we can actually see the melt pool, and we can see the melt pool at the instance that the ultrasound wave reaches the melt pool and scatters. And so we have the ability to map the ultrasound signal through the X-ray extremely precisely, right? So in these experiments, we're doing 100 X-ray frames for every 25 ultrasound pulses, right? So every fourth X-ray frame corresponds to the precise instant that an ultrasound pulse reaches the melt pool. So I'm going to go through some results, and I'll show a video after this slide, but I want to give you a soft introduction into the results. So on the left-hand side, this is one X-ray frame. There's a laser that's coming down. It's melting the top of the material. It's creating a little tiny melt pool, right? So inside this region, it's kind of hard now because it's only a single frame. Inside this region is liquid aluminum, right? The laser has been on for 250 microseconds, and so there's a melt pool boundary. And then we come over here. This is the analogous result as I presented earlier with the thunder and lightning analogy. So we have arrival time of the ultrasound. We have experimental time, and so this is milliseconds. And so the laser turned on at this point, and the current time amplitude response is this far edge here, okay? And so the signal that we see at this point exactly corresponds with the scattering of the melt pool over here. Okay? And so the video that I'm going to show shows the dynamics of this. And so this is going to get deeper. It's going to be highly turbulent and dynamic. And before I go there, I want you to imagine what this might look like as time evolves. So the laser is going to be on for 4 milliseconds, and we're going to be recording the response at each of these times. And so remember what I said, when the melt pool gets closer to the sensor, what happens to the arrival time. So now I'll go ahead and play the video. I think I need to remove my laser pointer to do that. So the laser is off right now. The laser is going to turn on at 1 millisecond. This is the ultrasonic response. The laser's on here. We see melting. You can kind of see the liquid formation there, the corresponding signal. And then something special happens where we form this keyhole melt pool, right? So we form a vapor region. And again, this is problematic in 3D printing. Typically, we don't want this because this leads to porosity. but look at the ultrasound signal. So you can look at the ultrasound response and see a time history of the very dynamic behavior of the melt pool. Right. So the laser turns off here, and you can see the ultrasound signal returning upwards, right? So the solidification front is moving upwards. It's getting farther and farther away from the sensor, and then the end of it, right? So there's a lot of information contained within the response. So the melt pool is growing through here. So we see a decrease in the time of arrival. We see fluctuations. So the melt pool depth is going up and down, up and down. We can see that in the ultrasound response. And then when the laser turns off, we can track the ultrasound response and get information about the solidification, right? So going back to the original questions that I was asking, can we sense solidification? Can we sense hot cracking and things like that? So qualitatively we can do that. Let's look at some of the more quantitative results. I'm going to focus mostly on the solidification part. And so I'm going to shift the time axis. I'm going to say the laser is off at 0 milliseconds, and it takes about 0.6 milliseconds to solidify. I'm going to be analyzing this region. So what we can do, simply my student traces the perturbation to the earliest ultrasonic arrival, and we can get a line like this. We can plot that, right? So that's these blue lines in here. And then from the X-ray data, we can plot the depths of the melt pools, and we can put those over top of each other. And you can see the very, very nice correlation between the X-ray depth and the depth recovered from the ultrasound. Right. And then if we focus on the solidification happens at this point, and you can see kind of different slopes. And so that means different solidification rates are happening. So if we look at those slopes and the slope, the melt pool depth versus time, we can get solidification rates and look at which is an important parameter in how the microstructure forms. So our solidification rates from ultrasound is very much agreeable with what's recovered from the X-ray and what's in the literature. We can also look at other features in the melt pool. So if you look at what's happening here, this is actually cracking that's happening. So hot tearing or hot cracking. If we look at the signal before the melt pool was formed, before we have the cracking, that's the black signal. The red one is afterwards. So this red response is the scattered response from this region that contains the cracking. One nice result that I want to highlight is that we can look very closely at the time amplitude signal for this particular case. This particular case, we had a porosity that formed at the very tip of the melt pool, and then cracks grew from that. So if we look at the part of the signal that corresponds with the time where scattering from the pores happen, that's in the gray windows. And you can see not much change in amplitude, right? So we get a pretty constant amplitude from scattering from these pores, and then the cracks form and grow. So the volume of these cracks increase and comes a little bit later in time. So these cracks are further away from the sensor than these pores. We see an increase in amplitude in the pink portion of these curves. So just to highlight, this is really a nice look of how we can use acoustics at very, very small length scales. So this bar is 50 microns, so very, very small length scales, but also very, very fast times, right? So there's only 0.08 milliseconds between these frames, and we're able to capture the evolution of these cracks. Okay, so those were the primary results. I hope I gave you some insight on both the 3D printing of metals and how we're using acoustics and ultrasounds to better understand some of the fundamental and foundational behavior in this area. So I'll hold off questions for now, and I'll turn it back to Ying. Thank you for your attention.
Okay, Chris, thank you for your excellent talk. Very interesting development. I have a lot of questions, but let's hold that for the panel discussion. So our next speaker, Professor Ying, he's a full professor and doctoral supervisor at the School of Physics, Nanjing University. He obtained his bachelor and doctoral degree in acoustics, both from Nanjing University. His research mainly focuses on sound field control, acoustic metamaterials, and acoustic functional devices. He has published over 100 papers in high-impact journals, including Natural Materials, PRL, and Natural Communications. With over 5,000 citations, he has a high index of 36 and has obtained more than 10 national invention patents. Professor Chen has been supported by National Science Fund of Distinguished Young Scholars and the National Outstanding Youth Science Fund. Additionally, he has served as council member of Chinese Acoustic Society and vice chairman of professional committee of acoustic detections. And he's also an editorial board member of Journal of Physics D and Applied Physics. Professor Chen, it's your stage. Thank you.
Thank you. Can you hear me? Can you hear
Yes.
me?
Yes.
I hope the Zoom works well now. I will show my PPT. Okay. Can you see my screen?
Yes.
About now, it's okay.
Looks
Okay.
great.
Okay, thank you. I'm sorry for the time. Thank you, Professor Liu, and thank you to the Acoustics for having me today. Hello, everyone. My name is Ying Cheng, and I came from Nanjing University. Today, I'm going to talk about acoustic metamaterials and device design. Before we start, let's take a quick trip through history and peek into the future. Acoustics is one of the earliest subjects in physics. Think about it thousands of years ago. Our ancestors were already control sound fields with cleverly designed structures. Take architectural acoustics in ancient theaters, for example. They were like sound filters, making sure people in the back row could hear the play clearly. Now, acoustics is still lively and relevant as ever. In fact, modern acoustics is crucial for national security and our daily life. But no matter how you look at it, there is always this big challenge: the precise control of acoustic fields, and that's what we are going to explore today. I think it's cutting edge stuff in this fascinating world. All right, let's start with a bit of background. Acoustic metamaterials have been stealing the spotlight for the last 20 years with their mind-blowing properties. It all starts with a very simple idea: imaging using tiny man-made microstructures that sound waves can't see to replace the atoms in natural materials. That's the core of the metamaterials. And the magic lies in those basic building blocks: by tweaking the way sound waves move from or through these spatial structures, we can create acoustic properties that are way out of the ordinary, but still within the laws of the classical acoustics. To show you how cool these properties are, let's talk about two key acoustic parameters: a dynamic density and a dynamic elastic modulus. Think of them as a map of four zones. Regular materials in nature can only be found in the first zone, where both the parameters are positive. But with our clever microstructures, we can explore the second, third, or even the fourth zones. That means we can get negative equivalent dynamic parameters, or even parameters that were close to the zone, to zero. And guess what? And we can, these unique properties are like a toolbox for all sorts of amazing applications, from surveillance imaging to sensing. That's to name a few. And we will focus on a point of, in them. Okay, let's talk about something very cool. The topology. Topology is like a branch of math that deal with things that stay the same even when you mess with them a bit. And in 2016, three scientists won the Nobel Prize for figuring out about topological phase and topological transition of matter. That's a very big deal. One of the truest discoveries in the 21st century is topological insulator. It's like an insulator in the middle, but a conductor in the edge. Think of it like a movie about a quantum Hall effect, where electrons travel along the edges. This could be a game changer for energy consumption and heat dissipation in those tiny high-performance integrated circuits. And it has tons of potential for low-power devices and quantum computers. Okay, now let's get even more exciting. What would happen if acoustics and topological states got together? Let's dive into a challenging topic: the new physics of acoustical localization and detection. At first, these two things have nothing in common, but we are going to blow away what we are talking about next. All right, let's tackle three questions together. Question number one: what's the use of acoustic positioning and detection? When we talk about modern ways to pinpoint and detection, people usually think of GPS, Beidou, or Galileo. All these things use electromagnetic waves. But did you know that acoustic positioning is a very big part of our daily lives? It is not just about radio positioning. It's in that, for example, car horn honking on the streets, finding out where a machine is faulty, or even that backup beep in your cars makes when you are reversing. And let's not forget its unique applications for underwater animals detections and navigations. Now, how do we make this work with the technology we have? Well, one big challenge with sound is that it diffracts a lot. That's why we can hear sounds coming from all around us. Think of a noisy room with a lot of speakers talking at once. it's hard to make out what your friend is saying because of the low signal to noise ratio, and you can't even figure out where they are. That's the problem. And then there are those martial art stories where masters can use whispering transmission, a skill that will emit sounds that only one person can hear. It sounds like legends, doesn't it? But can we really do that with science? We'll get to that soon. All right, let's talk about how we can make sounds work better in our daily lives. One useful way is to modulate sound signals onto ultrasonic carriers. This basically means we can create a sound bubble in a noisy place like a hospital or train station without disturbing anyone else. It's like having your own private sound zone. Another method is using phased arrays. You might have seen this in smart speakers, acoustic cameras, or sonars. It involves putting a lot of sensors units in a space and control each one's volume and timing to create a focused beam. But these systems are often very big and very complex. And that's where the traditional beamforming technology comes in. The challenge is to get high directionality and spatial gain with a small setup and fewer elements. It's like trying to make a laser beam with a dim flashlight. So we have question number 3. What new tricks are we going to learn in the future? We are on the brink of some amazing discoveries in the sound technology. The scientists often draw inspiration from nature, and dolphins are a good example. These marine mammals have a unique ability to create really focused sound beams, like a flashlight for sound. They can aim these beams at a narrow angle of about only 16 degrees to hunt for prey in complex environments with high precision. But as humans, we don't have such specialized features. So we are struggling to mix and hear some signals with the same focus. So what's the novel solution? Well, we are working on enhancing our sound sensing ability to make them more directional, sensitive, and with a better signal-to-noise ratio. One cool example is this thing called audio lasing in a non-emission topological whispering galleries. You might have heard of the whispering galleries before. It's that weird acoustic phenomena. Imagine one where you whisper on one side of a curved wall, like in St. Paul's Cathedral in London, or the echo wall of the Temple of Heaven in Beijing. The sound travels along the wall and can be heard clearly on the other side. That's because sound waves bound around the smooth cube with little loss, traveling a long way. This principle can actually help us capture weak sound signals, making it easier to detect and transmit them. Over the last half century, the whispering gallery modes has really shaken up the world of optics. Think of it as a super cool trap for light in tiny space, just a micrometer big. This trap lets light and matter interact in ways we've never seen before, which is like the secret source for all kinds of optical gizmos. It's opening up all sorts of possibilities for scientific discoveries and technological breakthroughs. And it does not just science fiction. We are already seeing real-world applications like quantum computer storage and uncopyable anti-counterfeiting systems. Recently, we've been playing around with combining topologically protected edge transmission with non-Hermitian system. The result is a topological laser that performs like a dream. But here is catch. Acoustically, we are kind of stuck. Without the right kind of acoustic gain medium, it's tough to create non-Hermitian acoustic topological structure. Right now, our one-dimensional non-Hermitian acoustic system are sort of like toy versions using speakers for simulation. And in 2 dimensions, we are dealing with medium with loss energy at different rates, which is not ideal for controlling high-dimensional acoustic fields. So our mission is clear. We need to dig out deeper and find those hidden, unique whispering gallery modes in non-Hermitian topological physics. It's let me show you how we are aiming to achieve an amplified acoustic lasing mode. We've introduced an active fluid layer into the mix. This layer has a special trick. Its imaginary part of the effective mass density can be tweaked using a non-Hermitian gain factor. Picture just think a triangular assume a triangular lattice made of rigid trimmers, and these trimmers are coated with this active layer. Without inverted symmetry, the Dirac degeneracy gets lifted. Now, if we zoom in and see the Venn diagram, we find that the valid states K1 and K2. We can see that the negative imaginary part of the eigen frequency is really responsible for sound amplifications. Furthermore, we can see that in the Venn diagram of the ribbon structure, the real parts show us the topological edge states exists in the band gap, and the imaginary part tell us that these edge states undergo sound amplification along the interface where when the gain is present. But the real challenge here is achieving that acoustic gain. So we know that loudspeakers with right gain circuits or acoustic electric effects can do it. But there is a more flexible and tunable way. It's called thermoacoustics, where fluctuating Julie heating is transformed into sound. This electro-thermoacoustic coupling is seriously efficient in carbon nanotube films. Now, the question is, how do we combine CNT film with sonic crystals? We use 3-dimensional printing to create rods made of ABS plastic with 2 voids inside to cast the electrodes. These electrodes connect to the CNT films wrapped around the rods. We assemble several rods into a triangular lattice and mount it onto a PCB board. By carefully designing the circuit, we can independently control the phase and amplification amplitude of the sound waves radiated by the 3 rods in each unit cell. That's like in the figure. That's the gist of what we are doing to amplify acoustic lasing mode. They are very simple. There's a lot of science and technology behind it. All right, let's dive into the world finite sonic crystal. First, we need to understand the CNT film a bit better. We did some experiments to compare how the CNT film and a regular paper basin speaker react when excited. Using a microphone and a laser vibrometer, we measured both the acoustic and vibration signals. You guess what? The acoustic pressure amplitudes were pretty much the same in both cases, but the CNT film hardly vibrated at all on its surface, while the paper speaker was shaking like crazy. This just goes to show that the CNT films create sounds through thermoacoustic coupling, not by traditional vibrations. And speaking of thermoacoustics, we also measured the CNT film's electrical impedance. It turns out that the film is basically a resistor with a very fixed resistance over a wide frequency range. Plus, we can see that how sound spread from a single closed rod within the band gap. The sound went in all directions evenly. Means that the CNT film is really uniform. To really see the thermoacoustic effects, we use an infrared thermal imager to take pictures before and after applying currents. The results looks very clear. But there is also more. We've also built an acoustic non-Hermitian whispering gallery structure that's topologically protected. And for the first time, we discovered these independent gallery modes. The breathing modes, the counterclockwise mode, and the clockwise mode. So as you can see, we are not just playing around with sound here. We are exploring new ways to create and control it using cutting-edge materials like CNT films. All right, let's dive it in this theory a bit deeper. To test it, we did some numerical calculations on the amplification factor, just considering different gain phase texture. Amplification is how much louder the sound is along the whispering gallery compared to along the straight domain wall. Looking at this rainbow colored map, it shows that the sound intensity along the lower domain for waves go right or left. The counterclockwise and clockwise mode are shown here. Now, when the gain phase texture is 0, we only see the chiral breathing mode. But as we increase the phase texture to pi, 2 more whisper gallery chiral modes pop up. And when we hit 2 pi, the breathing modes disappear and the other 2 take over. The experiments on the right match our simulations perfectly. So, of course, we can't quite separate the different chiral whisper gallery modes in this experiment, but we will figure out it later. Now, let's talk about how robust the system is. We simulate defects in the corner or side regions, and we see that the frequency and the amplification of both the counterclockwise and clockwise modes are still pretty much the same as when there are no defects. So our theory stand very strong, even when we introduce defects. That's really a good sign for its real-world applications. All right, let's see how we can split and identify the different priorities in our experiments. Let's talk about the gain phase of 2π. We measured the pressure amplitude at both router ports, and we can see that different clockwise Western Gallimos output through different ports. Now, for example, when the texture is 0, the breathing mode goes out in 2 directions from 2 ports. But when the gain texture is 2π, the clockwise and counterclockwise modes can be separated efficiently, and we can get really directional emissions that looks like needles. The story has really captured the attention of scientific community, with headlines like gain medium gives a boost to sonic crystals, Caesar, or Caesar, unprecedented breakthrough. But let's dive a bit deeper into what we're working on. Besides the exciting advancements, we've also been busy studying on how our systems stand up to environmental noise. Imagine this picture. When there is noise source out there, out the speaker, very loudly. It's like the noise is shouting over the top of our signal, make it hard to hear. So what can we do? Well, we built a topological acoustic antenna system that uses the special ability of acoustic wave topological boundary states to block out the unwanted noise. It's like having a super focused ear that can hear exactly what we want and ignore everything else. And when it comes to sending sounds, this system is also very amazing. It makes sure that a sound only goes to the person we want to hear it, and no one else. Compared to the old school technology, the pin is much narrower, down to just 9 degrees, and the main port of the sound is about 97% of it. That's a very big step forward for secure acoustic communications. Okay, let's do something more. This antenna can help us to pick out the specific signals from a noisy background. In our experiments, we use a loud, messy noise source and to try and mask the signal we were looking for. It was like trying to find a needle in a sea, but with our antenna, we were able to clearly hear the target signal, even when it was buried deep in the noise. So not only are we making strides in science, but we are also developing real-world solutions that could make a difference in how we communicate efficiently and securely. Moreover, drawing inspiration from that, our international colleagues have gone on to replicate the similar functions in a range of settings, from underwater to solids. Moreover, recently, we've even taken a shot using micrometer scale, ultra-narrow directional sound beams in solid devices. The goal is to separate circulating tumor cells from healthy cells, one by one, with precision. Very exciting. All right, let's now sum this up. in a very quick way. With the potential of new physical mechanism on the horizon, we are looking at breaking through the barriers of current technology. This kind of boost in sound localization and detection may open up a new world of possibilities for our daily lives in the future. But we still got a lot of work to do to make this new physics a reality in real-world applications. We are like those, we want to work like those diligent ants, working hard to bridge the gap between physics and practice. That's all from me. Thanks for listening. Thank you.
Many thanks, Professor Chen, for your excellent talk. It's really interesting. Today, okay. Today we have three very interesting speeches from Professor David Zheng, Professor Chris Kube, and Professor Ying Chen. Professor Fan talked about, he developed many interesting and powerful imaging, ultrasonic imaging technologies. And Christopher has great development for additive manufacturing, monitoring, inspection with ultrasonics. And for Professor Chen,
Hi, Yang.
Hello.
I must mention you. Go back 2 slides. You have to introduce your panelists first, okay?
Okay.
First,
okay.
you go back. Zheng and Tom couldn't be, skipped.
Sure. Yeah. So we also here we welcome our panelist, Professor Zheng Tu from Nanjing University and Professor Chang Su from Institute of Acoustics. I think after we have gone through the three interesting talks, and you guys should have many questions. So, what's your question? Do you have any question, Professor Tu?
Okay, well, definitely interesting talk, and of course I have some questions to the speakers. So maybe I can do like one by one. So the first question is to David. So is that okay, David?
Yeah. Let me turn on my camera. Right. Okay. Yes.
As you give us some introduction about the NDT technology and its applications in a lot of areas. So as introduced in your report that we have a lot of, we can use NDT to detect defects in materials. But actually in recent years, now we have some other new materials and novel technologies like 3D printing and some extra thin material, something like that. So can you give us some comments about how can ultrasound technology, including NDT, play more critical role in the design, preparation, or characterization of those kind of new materials or new modalities?
Sure. Yeah, I think actually Chris just gave a talk. His talk is mainly on how to monitoring the process of 3D printing. This is one of the very good application of ultrasound that you can monitoring the process of a new manufacturing process. For ultrasound, we also think it can be useful for detecting the material properties in the new materials, because what industry is interested in is actually what are the mechanical properties coming from the new process, and then with ultrasound we are able to understand a little bit of elastic properties. So there could be some research doing to correlate those ultrasonic signals with more complex materials. For example, could be anisotropic and inhomogeneous material. For example, in aerospace industry, there's a lot of structures could be these kind of materials, and these definitely create challenges for the inspection, and also at the same time bring opportunities for ultrasound to infer those material properties, that if we can build up certain correlations with ultrasonic signals with respect to the material properties, then definitely opens a door for industry to do a lot of quality control. This is one aspect. Another thing you mentioned about new materials, one example I can think about is, for example, batteries. Currently, there's a lot of EV batteries in the world developed, especially in China. There's a lot of EV cars in here, and then I believe in a number of years' time there will have a lot of retired batteries, and whether we can using ultrasound to make a bit of diagnosis of the state of health of the EV batteries, that could be a very interesting topic. But that's again, that will be challenging, because this is a very complex materials. It has multi-layers, and also the material property, it has multi-layers consisting of solid, consists of porous material, consists of liquid. So ultrasonic signals in these kind of materials could be very complicated. I believe there are a few researchers over the world, including our group, investigating some of the properties of ultrasound when it go through these battery materials, try to correlate with the state of health and also possibly state of charge of batteries, because that's quite interesting. But also not only the material is material property is complicated, but also the process, the electrochemical process is also not fully understand. So I think there's a lot of room for us to research in these areas, including the very recent hot topic solid state batteries. There could be opportunities for ultrasonic-based diagnosis methods to correlate to these material properties. So that's a bit of my thoughts on that. Yeah.
Okay, thanks. I think
Thank you.
It's a very interesting and exciting future we can have for
Hope so. Yeah.
development of NDT new technology and for our future life. And I can have a relative topic, a question to Chris, because you are talking about NDE, because it's really a wonderful talk about high-speed ultrasonic diagnostic of the metal additive manufacturing, melting pools, those kind of. But since our topic today is exploring the frontiers of acoustics, so maybe can you give us some general comments about the potential challenges and the opportunities for the frontier advances of this kind of NDE studies? Because David has already told us something, but can you have some further comments about that, or like something like the powerful AI tools is very hot topic recently? But do you think this kind of AI tools can be used for the innovation of the NDE or NDT technology?
Yeah, thanks for the question. So in my talk, I gave a demonstration of using ultrasound where we have a direct comparison to the high-speed X-ray image. So the X-ray image allows me to figure out what's happening in the ultrasound signal, and we don't always have an X-ray source to compare to, right? And when I think about AI, that's going to enable new modeling techniques, right? So potentially we can model the melt pool and how the ultrasound scatters and have a comparison right on our computer. So I don't have to travel to a $1 billion X-ray facility to determine what to expect in the ultrasound response. And so I think moving forward, especially when materials get much more complicated. So remember, acoustics propagates through materials, and the waves are strongly perturbed by the internal structure of those materials. As materials get more complicated and complicated by design, right? We're designing materials for new functionality, and to do that, they become naturally more complicated. So in order to interpret ultrasound responses and enable the characterization that David is talking about, or what I highlighted with the X-rays, we could use AI tools to help that understanding. So it's going to be a interesting time moving forward, and kind of this partnership between AI modeling and the experiments that we do. It's going to be very exciting.
Do you like the AI tools?
Absolutely. Yeah, for sure. I've already used a couple chatbots this morning for various things, so it's
okay. Yeah, maybe we can discuss later. Maybe we can learn something from you.
Yep.
Okay, thanks. Actually, compare with the previous two talks, and Professor Zheng's talk is more physical. It's close to the fundamental physics. It's more like physical acoustics study. But I'm kind of a little bit lost about it. Professor Chen said you can make high directional acoustic radiation force by designing some special acoustic metal surface or metal structures or some other designs. But this looks more like the simulation or those kind of studies. Can this phenomena can really be applied to practical acoustical scenarios? So Professor Chen, can you give us some idea about how to use this technology in our real life?
Okay, thank you, Professor Chi, for the question. I'm sorry about that. My talk is very very physical, focus on physical acoustics. In fact, we are exploring the physical principle of obtaining beamforming in a novel way. You mentioned that how we can implement it's in acoustic communications. I think high directivity directional acoustic radiation beams have very broad application prospects. For example, we not only in the audio sound, in airborne acoustics, but also in solids for electric waves. For example, we are trying to develop a solid device with the capability of focus the acoustic surface waves with the beam width in a width of sub minimum watts. So if we can do this, and we can okay. I think one of the important technological foundation for cell screen is the realization of high directivity of these ultra narrow acoustic beams on the microfluidic chips. That is very difficult to achieve using traditional acoustic techniques. So we are currently studying the use of the methods we mentioned above, on chip acoustic technology. to achieve such acoustic beams. And I think in future to achieve high precision separation of circulating tumor cells and normal cells. That's an example of what we can image in the future. I hope make it clear. Thank you.
So let me see if I answer understand your your talk correctly. So you mean that we can imagine that maybe my friend and me sit in different position in the same room, but the same room, then we can hear different sounds or particular sounds we like. So you can deliver like particular sounds to different person, right?
Yes, we can deliver the sound to the specific position or the specific person. And in reverse, we can also hear the sound from specific person. And while we neglect and all filter the noise from other directions. That's very useful, I think, in the architectural acoustics.
Oh, that's great. So that's really fantastic. So that's all my questions. Yeah, thanks, Professor Liu. Yeah.
Okay, so Professor Su, how about your questions?
Yes, okay. I also have 3 questions for each of the presenter. So my first question is to Professor Fan, David. And it might be a more general question because all the 3 talks today actually had something to do with wave propagation in complex media, either containing microstructures or with multi-phase media, including fluid and solid and air. So today's topic is the frontier of acoustics. So I suppose this is one of the frontiers of acoustics. So I want to hear what's your comment about this, and what do you think could be the future application of these complex phenomena of wave propagating in these complex media?
Try to understand your question. You are trying to say, what can we do with when the media is complex? We want to reconstruct information from the media, or
we can either reconstruct to image the structures, or we can use the phenomenon, use the propagation characteristics to do something else, maybe manipulating. And since you also include something about the using of ultrasound energy to manipulate little particles, so I want to hear your comment on this.
Right. Yes, I understand. So one way that we can harvesting the energy to for some other use, like we present tweezing. We all know that optical tweezer has won Nobel Prize several years ago. Then acoustic tweezer definitely have the room to play when we want to control particles. But maybe we need to do a bit more, especially in a biofield when we want to control different cells in a more accurate way. That's one thing. We could also possibly do levitations, utilizing acoustic waves to levitate particles to like the remote handling. That could be useful in certain scenario, I think. Also, in the medical field, we can consider something in the medicine and therapy. Professor Tu is an expert in this. So how to do target drug delivery, like non-invasive surgery, stimulating using focused ultrasound, high-intensity focused ultrasound to destroy tumors without damaging the surrounding tissues. That could definitely can be done. And another area I see some of the researchers in the world is doing is possibly using ultrasound for rejuvenation, like the battery issues we mentioned. There will be a lot of retired battery in the years to come. And using ultrasound and other stimulation method, you can potentially recover certain of the energy from those batteries to make certain things reversible. That I think is very advanced to me. I don't know exact mechanism behind, but certainly it will be very interesting to look into this if there are opportunities. Yeah, so that's my thought. Thank you.
Thank you. So yeah, ultrasound and acoustics has a very wide application in our daily life, actually. So my second question is to Professor Kube, and I think in your presentation we've seen that acoustic is used together with other physical modalities such as X-ray and maybe heating, or sometimes we also see acoustic used together with the electromagnetic waves. And what do you think are the unique advantages and the disadvantages of acoustic waves? And how do you think we can make better use of these an intersection of acoustic together with other physical modalities? So this is my question.
Yeah, so that's a very nice question, and thank you for that. So my first thought when comparing acoustics with other forms of say electromagnetic radiation, acoustics has the ability to penetrate deep into highly dense materials, right? So in my presentation, I showed high power X-rays. These are some of the most highest power X-rays that people can develop. And even those can only penetrate through metals a few millimeters. And so throughout the talks, there's many examples of how ultrasound can propagate deep in materials and study the interior. So that's one of the major benefits of acoustics and ultrasound that can be leveraged. As far as looking at the combination of acoustics and other techniques, I gave a talk about how they can be used side by side to help understand the acoustics, and then you can imagine having the acoustics tool by itself. And so I think as science evolves in all of these different areas, there's going to be a handshake between methods that can help develop them individually, and then those methods are validated and can be used where their individual strengths really shine. So I guess that's my take on that. So thanks for your question.
Thank you, Dr. Kube. And for the third question for Professor Cheng, yeah, I think I kind of agree with Professor Tu about the concern of how the metamaterials can be used in real application. And but I'd like to ask another question. Since in your presentation we've seen interesting physical phenomena created by these acoustic metamaterials, so they can be unconventional. Sometimes they are even against our intuition. So could you give a little bit more explanation about are these phenomena against our traditional or conventional physical facts about acoustics? And so what's your comment on that? And yeah, and what's the main challenge in this field, in the metamaterials or metasurface field?
Okay, thank you.
Go ahead.
Okay. Thank you, Professor. I think that's very interesting and very important question. I think, to my knowledge, the phenomena itself looks like against the basic laws of classical acoustic, but in fact, the acoustic properties we create also follow the basic functions. For example, the acoustic functions. We can understand it in a different way. For example, I just mentioned that we can create negative mesh and negative elastic modulus. I just give a word before that, the dynamic. It means that we are not mentioning the static mesh and static dynamic static elastic modulus here. We are talking about what we are talking about is the dynamic response to acoustic waves from the medium or from the microstructures. In fact, we inside the microstructures, all the classical acoustic theory can govern the individual response of these microstructures. But as a whole, the coupling from these structures and coupling from and interacting from these areas will create very exciting dynamic responses. So I don't think that that manage the classical acoustic theory is another it provides a new vision for the traditional acoustic theory. That's my understanding. Thank you.
Thank you, Professor Cheng. And yes, it's a really interesting topic. And that's all my questions to Professor Liu.
Okay, thank you. Thanks a lot for all our speakers and the panelists. I think today I learned a lot really for the frontier of acoustics. Since we have already ran over the time, I think we should conclude. I mean, this today's forum. I mean, thanks again. So.
Thank you.
Thank you. Thank you, everyone.
Thank you. Thank you.
先生、女士们、亲爱的朋友们，欢迎大家来参加我们的 ICANX 达沃斯科学峰会。那今年是第一次 ICANX 会组织大家一起在瑞士的达沃斯进行线下的聚会。我们有6个主要的议题。第一个是创新 innovation， 第二个是科学 science， 第三个是 technology 我们的技术，第4个是 investment 投资，第5个是 management 管理，第6个是 entrepreneurship 创业。所以它结合起来就是 It's time 是时候了，是时候让我们去达沃斯听这些非常 给我们启发的关于未来的这些报告。在达沃斯我们会有3个非常重要的论坛，一个是诺贝尔奖论坛，我们会邀请诺贝尔奖获得者来跟我们谈科学的未来，我们会邀请世界科学院的院长来跟我们谈世界科学技术发展的未来。那我们会邀请大学校长来参加我们的世界大学校长论坛，来跟我们谈关于教育的创新教育的这样的一个未来。同时呢，在达沃斯呢，我们也会邀请各行各业的这样的一个非常重要的领袖人物、领军人物来跟我们分享他们的所思所想，他们对未来的思考。那我们也会邀请非常多的各行各业的精英来跟我们分享他最精华的这样的一个思想。那当然了，达沃斯这个舞台也不只是给这些大牛们展示的舞台，也是我们来展示的这样一个舞台。所以如果你有好的故事、好的思想、好的技术、好的思考来进行分享，那也欢迎你再来线上投稿。所以我们的截止时间是4月1号，大家还有1个月的时间来准备好你的发言，希望分享给全世界的。所以欢迎你在线提供你的资料。那我们也希望你成为这个舞台上的明星。那在达沃斯呢，我们设了3个奖，第一个是针对大学生的，你是创新创业的最牛的大学生，那你来申请我们的创新奖。如果你是一个毕业10年以内，现在正在从事独立科研工作的科学家，那你来申请我们的青年科学家奖。如果你是一个创业者，你成立了你的公司还不到5年的时间，已经发展得非常好，那请你来申请我们的创业奖。所以所有的奖项申请的时间截止都是4月1号。那欢迎大家在线提供这样的一些资料，那我们也会给大家非常多的这样的机会，成为舞台上最亮的星。那是时候来我们大家一起把科学推向未来，推向世界。那这个呢是我们在达沃斯的非常重要的合作伙伴，我也希望你成为我们的合作伙伴，我们一起来推动世界的发展。那现在达沃斯论坛已经开始注册了，所以各位朋友、各位好朋友们，请你们开始尽快注册吧。我们相聚在达沃斯，我们一起 Go Summit 走向巅峰。
祝你生日快乐！该吹蜡烛了，来，我帮你。啊！祝你生日快乐！生日快乐！
好漂亮的花，我很喜欢。
这是我的礼物，多层陶瓷电容器。
哇，这是多层陶瓷电容器吗？
失败了，没新意。那个我的也是啊。